I want to cover a few more things on plate tectonics. So I'm going to use this as kind of a review, but I'm going to add some information as well that wasn't covered under the initial lectures. So just to recap, plate tectonics is probably one of the most important topics that we're going to cover in this part of the course, because it is, it goes along with volcanism and tectonism, but most of volcanism and tectonism is driven by plate tectonics. So hopefully you watched the film Ring of Fire, and the Ring of Fire was really about plate tectonics, but they kind of worked their way backwards. They talked about volcanoes and then earthquakes, and then they kind of worked their way back to see that those were an intricate part of this worldwide system of moving tectonic plates. So the lithosphere is broken up into segments called plates, the lithosphere being the outermost kind of rock layer of the Earth. And then they move over something called the asthenosphere, that underneath the really solid part of the Earth, it's more of a molten part. There's convection currents that move, and they drag the outer part of the Earth along with it. And so these plates are in movement. They're in very slow movement. It's about 1 centimeter per year. It's about how long the speed of fingernail growth. But they slowly move over time, and in some places they're pushing against each other, some places they're pulling away from each other, and some places they're sliding past each other. So here's a kind of a side view. You have the molten asthenosphere, the more solid lithosphere on top. The lithosphere, there's two separate parts to it. There is oceanic crust, which is made of a dark rock called basalt. And then there's lighter continental crust made of a lighter material called granite. Granite, like a granite countertop, like the rocks in Yosemite. Granite is an intrusive igneous rock that forms under the ground, and so granite is very common. Granite is really the core of most continents. Now, here, this is the Atlantic Ocean. Okay? This is called the Mid-Atlantic Ridge, where there is a separation happening. So the Atlantic Ocean is actually growing wider over time as the plates diverge. They move apart from each other. On the other hand, this is an oceanic plate pushing into South America, and here, this is converging and it's subducting. So the oceanic plate, which is heavier and denser, is subducting down beneath the lighter continental plate. Now, one thing I do want to add that may not have been covered so well in the previous lecture is just some more history of plate tectonics. It really starts with the continental drift theory, and this is a guy named Alfred Wegener in 1915, early 1900s. He comes up with this theory of continental drift. And so he finds that there is, if you look, if you ever kind of look at a world map and you look at especially South America and Africa, it kind of looks like there are puzzle pieces that could fit together. He was fascinated by this. And most people kind of dismiss it over time. They look at this when they're a kid, they think it's something cool, but then they sort of dismiss it. But he didn't give up on it. So he actually went out and found evidence that, hey, in reality, Africa and South America were at one time connected to each other. There's evidence in the fossil record, there's evidence in the rock record that various continents at one time were together into one supercontinent. It was called, that he labeled Pangaea. Pangaea being a former supercontinent. So fossils, rocks, and so on. And at the time, it wasn't universally accepted because that's just crazy. Like, how does a continent move? Like, what force could move a mountain, let alone a whole continent? So people didn't understand the mechanism. So his theory was out there, but what he didn't understand was the mechanics of it. How does the Earth move these things around? So here's some examples of some of the evidence. Evidence of glaciation that is common through various continents that were at one time connected to Antarctica. Different deposits of different materials that seem to be contiguous across continents. And also records of fossils that suggest that at one time these fossils were of species that were in a continuous landmass. All right, so we didn't understand how this worked. And so in the 1950s, this is during the Cold War between the Soviet Union and the United States. And one thing happening around that time was an intensification of submarine warfare. And to make that work, because of the amount of submarine warfare, there was a really intensive mapping of the seafloor to help navigate and understand what was happening below the water. And so it's only when people see what is the topography of the landscape below the oceans that they really start to get a better handle on what the plate tectonics as a whole, because much of the evidence is underneath the water. Here's some examples that what they found when they started using sonar, type of remote sensing underwater, to map things out. They found deep trenches in some places, like the Aleutian Trench. If you watch the Ring of Fire video, they were discussing the Aleutian Trench in Alaska. It is a deep trench where subduction is happening. And they also found these mid-oceanic ridges, these sort of mountainous landscapes in the middle of, for example, the mid-Atlantic ridge where the Atlantic Ocean is growing, and there's a kind of a development of these little mountains along the ridge where the growing is happening. And so they mapped these things out on the seafloor, and what made it more interesting is that when you plot where earthquakes are, the earthquakes align to these trenches and ridges. So that pattern suggests the process, that they see that they find these features on the ocean floor, and then coincidentally, there happens to be earthquakes all around there, and they're starting to understand what is going on. So the first thing is seafloor spreading, that you, at these mid-oceanic ridges, see the redder colors are showing you the youngest rocks. And so that there is brand new rocks happening in the middle of the ocean, and then those are moving away and becoming older and older and older. So there's a way that they were able to test these rocks and understand that the new ones are right along where the separation is happening, and they get older as they move away. So, for example, in the mid-Atlantic ridge, because the Atlantic Ocean, again, is widening over time. Where you have the trenches, what's happening there is subduction. Subduction is where one plate is being pushed underneath the other, and because the oceanic plates are heavier, they subduct underneath the lighter continental plates. And then that plate is then melted underneath the earth and recycled. Okay, there's 3 types of plate boundaries, and I think I went over these, so I'll just go through them quickly. There are divergent plate boundaries, like in the middle of the Atlantic Ocean. There is convergent boundaries where you have subduction. And then lastly, there's transform boundaries where things are sliding past each other, like the San Andreas Fault. So divergent boundaries, this is where you have seafloor spreading. So the Atlantic Ocean is a good example of a divergent boundary, because at that boundary, the Atlantic Ocean is separating and growing wider. They're mostly in the ocean, but you do have some examples on land. So for example, in Africa, you have an area called the Continental Rift Valley where the land itself is being pulled apart. Then we have convergent boundaries, and there's 3 different ways you can have that. You can have oceanic crust colliding with continental crust. Some cases you can have oceanic crust colliding with other oceanic crust. And then lastly, you can have continental crust colliding with other continental crust. So where you have oceanic and continental crust, you have subduction happening because the heavy ocean plate will subduct underneath you. And if you saw the Ring of Fire video, what they showed was a 3-dimensional mapping of earthquakes, and what they found is that you have earthquakes that are shallow like up here, but really other earthquakes that are deep within the earth. That's because of that plate being shoved way down underneath the earth. And by mapping in 3D these earthquakes, they can understand this process. So these are places where you have shallow and really deep earthquakes. The same goes for oceanic to oceanic crust, that here typically one of the types of oceanic crust will subduct beneath the other. And you'll have, if you look at this figure in the book, it kind of shows you in 3D as well. You have shallow focus to deep focus earthquakes. Now the third example is, you see it in the Himalayas, the mountain range north of India, that over time the Indian continent has collided with the European or Asian continent, excuse me. And as the two continents collide, they don't subduct because they're too light. So what they do is they crumple up and create a big mountain range like the Himalayas. So where you have subduction, you have very deep focus earthquakes and volcanoes. Otherwise, it's more of a continental collision. It's more just of a happening at the surface. You don't have subduction where two continents collide. And lastly, transform boundaries are where one thing is sliding past the other. And the best example of a transform boundary perhaps in the world is in California along our San Andreas Fault. And where you have a lot of subduction happening is along the Ring of Fire. So hopefully you saw the video. One place they were highlighting here is the Aleutian Trench. The Aleutian Trench, kind of that little arm that goes off of Alaska, is a major subduction zone. That's why they have all of the volcanoes and earthquakes. So the Aleutian Trench is the north end of what's called the Pacific Ring of Fire. This is the area with the greatest concentration of earthquakes and volcanoes. Now, one thing I should mention that wasn't in the earlier video is that you see volcanoes around. Let me kind of show this here, around here, but there's a few that are kind of off on their own, like in Hawaii, or the Galapagos Island, or an island here in the middle of the ocean. Actually, let's focus in on Hawaii, because Hawaii is a good example of a geologic hotspot. And we haven't covered this yet either. A hotspot is a volcano that occurs away from plate boundaries. And what happens is there's what's called a mantle plume. There is magma that rises from deep within the earth and creates a stationary volcano right in the middle of the ocean, far away from tectonic plates. But it creates it where it creates it, there is a plate that's actually in motion. So it's kind of a little factory. It creates an island, the island moves away, creates a new island, the island moves away. It's almost like a little island factory happening out in the ocean. So you have this mantle plume that rises, and the mantle plume stays the same, but the tectonic plates are moving over the top of the mantle plume. So the mantle plume is punching through, making an island, punching through, making an island, punching through, making an island. So it creates a chain of islands like you see in Hawaii. So here, for example, if you look at the Hawaiian Islands, the oldest Hawaiian island that's above the water is Kauai, about 5.1 million years old. And the newest one is the big island of Hawaii. It's less than 1 million years old and still has an active volcano. So at one time, Kauai was back here, but it got created and moved away. Then Oahu got created and moved away, and then so on and so on. So it's creating like a little island factory.